It should not exist. Before you can even begin to comprehend the scales involved, your mind rebels against the sheer paradox presented in this single frame of cosmic data. What you're looking at is impossible. A galaxy, a magnificent island of billions of stars hangs in the void. Yet just beside it, a ghostly twin resides, an ethereal echo of the first. And then you see another, not a twin but a distorted caricature, its familiar spiral shape stretched into a luminous, impossible arc of light. A fourth, a fifth, all phantoms of the same celestial object are smeared across the velvet blackness, like paint on a canvas that has been warped and folded by an unseen hand. Your eyes are not deceiving you, nor is this a malfunction in our most powerful telescope. This is the universe staring back at us through a distorted cosmic funhouse mirror. It is a genuine image of our reality, yet it feels like a dream. This single haunting photograph from the James Webb Space Telescope presents us with a profound enigma, a visual riddle that challenges the very foundation of how we perceive space-time and the act of looking. We have a name for this beautiful, baffling phenomenon. We call it a cosmic mirage. For millennia, we have looked to the heavens and assumed a simple contract with the cosmos, that light travels in a straight line. From the ancient Greeks charting the planets, to the first telescopes peering at the moons of Jupiter, this was the bedrock of astronomy. A star was where you saw it. A galaxy was as it appeared. The universe, we believed, was an honest broker of information transmitting its truths to us, across the vast empty darkness without deception. But here in this breathtaking image, that fundamental assumption is shattered into 1,000 glittering shards of light. The universe, it turns, in fact, a master illusionist. It is a lens maker of unimaginable power and scale. It bends, it magnifies, it multiplies what we see, creating phantoms and ghosts that are paradoxically more real and more informative than the simple direct view we once took for granted. This is the central mind-bending truth we have been forced to confront. The very fabric of the cosmos is not a passive stage upon which events unfold, but an active participant in the story, shaping the light that travels through it, and in doing so offering us a new and powerful way to understand its deepest secrets. How can this be? How can empty space, the very definition of nothingness, contort the path of light, the fastest thing in existence? The answer lies not in the emptiness, but in what fills it. The culprit is gravity. Not the gentle pull of a planet that keeps your feet on the ground, but gravity on a scale that defies human intuition. A century ago, a lone genius reimagined the universe. Albert Einstein proposed that space and time are not separate static concepts, but are woven together into a single dynamic fabric, space-time. He then made an audacious claim that massive objects do not simply sit within this fabric. They warp it. They bend it. Imagine placing a heavy bowling ball onto a stretched rubber sheet. The sheet curves, it dimples, it creates a depression. Now roll a small marble nearby. The marble doesn't travel in a straight line. Its path is deflected by the curve in the sheet created by the bowling ball. For Einstein, planets, stars, and entire galaxies were the bowling balls, and light itself, he predicted, was the marble. A beam of light from a distant star travelling across the cosmos for billions of years would have its path bent if it passed too close to a massive object, its trajectory altered by the gravitational valley carved into space-time. For decades, this was a beautiful but largely theoretical idea. We saw hints of it. During a solar eclipse in 1919, astronomers famously observed starlight bending as it passed by the edge of our own sun, providing the first dramatic proof of Einstein's theory. It was a monumental achievement, a confirmation that our understanding of the universe had fundamentally and irrevocably changed. But that was a subtle effect, a tiny deflection measured with painstaking precision. It was the equivalent of detecting a faint ripple in a calm pond. What we are seeing now, with the unprecedented power of the James Webb Space Telescope, is not a ripple. It is a tidal wave. It is the full, magnificent and terrifying power of Einstein's vision made manifest. In this image, the lens is not a mere star. The lens is a colossal cluster of galaxies, a cosmic supercity containing the mass of quadrillions of suns. Its collective gravity is so immense, so overwhelmingly powerful, that it doesn't just subtly nudge the fabric of space-time, it tears it into a complex landscape of peaks and valleys. It creates a gravitational vortex of such profound depth that the very geometry of space is twisted out of recognition, and the light we see, the duplicated and distorted images of that background galaxy, is the light of a far more distant object that happens to lie almost perfectly behind this massive galactic cluster from our point of view on Earth. That light which began its journey when the universe was just a fraction of its current age travelled for billions of years across the expanding cosmos, destined to pass us by unseen. But then it encountered this immense gravitational lens. As the photons streamed into this warped region of space-time, their paths were violently diverted. Some were bent to the left, some to the right. Some were focused as if by a magnifying glass, while others were smeared and stretched. The light from that single distant galaxy was split, fractured into multiple streams, each taking a slightly different path around and through the lensing cluster. And after traversing the warped space-time, these separate streams of light continued their journey for millions more years, until by a breathtaking cosmic coincidence, they all converged on a single tiny point in the universe, the mirrors of the James Webb Space Telescope. So what we see is not a trick of our optics, it is a trick of space-time itself. We are seeing one galaxy in one moment of its history, but we are seeing it from multiple perspectives simultaneously. Each ghostly image is a different view, a different path taken by its ancient light. The mirage is real. This revelation forces us to completely reevaluate what it means to look at the universe. We are no longer passive observers looking through a clear window. We are detectives analysing a distorted reflection to understand the unseen object that is creating it. The distortion, the very thing that seems like an imperfection, becomes the most valuable piece of information we have. It is a map. By meticulously measuring the positions, the shapes and the brightness of these lensed images, we can reverse engineer the lens. We can calculate the precise curvature of space-time it creates, and from that we can determine the exact distribution of mass within the lensing galaxy cluster. And this is where the mystery deepens, leading us from a mind-bending illusion to one of the most profound puzzles in all of science. Because when we do the math, when we calculate the mass required to bend light this dramatically, we find something astonishing. The visible matter, all the stars, the gas, the dust that we can see in the thousands of galaxies within the cluster, it isn't enough. It's not even close. The visible matter accounts for only a small fraction of the gravity we are witnessing. The vast majority of the mass, the overwhelming bulk of what is bending space-time and creating this spectacular mirage, is completely invisible. It is a substance that does not shine, does not reflect light, and does not interact with ordinary matter in any way we can directly detect. It is a cosmic ghost. We call it dark matter. For decades, the existence of dark matter has been inferred through the rotation of galaxies and the large-scale structure of the universe, but these were indirect statistical arguments. Gravitational lensing, especially on this spectacular scale, provides the most direct and visually stunning proof that this mysterious invisible substance is real. We are not just seeing its effects, we are mapping its presence. The beautiful ethereal arcs of light from the distant galaxy are literally tracing the contours of an invisible ocean of dark matter that dominates the cluster. The illusion the Cosmic Mirage has allowed us to see the unseen. It has turned the universe's greatest magic trick into its most profound revelation, giving us a tool to chart the invisible scaffolding upon which the cosmos is built. We are peering into the dark, and for the first time the dark is taking shape. But the power of this phenomenon extends even further, pushing the boundaries of what is possible not just in space, but in time. Because this cosmic lens is not only a map maker for dark matter, it is also a natural telescope of immense power. The intense gravity of the cluster doesn't just bend the light, it magnifies it. The faint ancient light from that distant background galaxy, which would normally be far too dim for even our best instruments to study in any detail, is brightened and brought into sharp focus by the gravitational lens. We are in effect using an entire galaxy cluster as our telescope's primary lens, a lens trillions of kilometers across. This allows us to see objects at the very edge of the observable universe back in the cosmic dawn, when the very first stars and galaxies were just beginning to flicker into existence. We are looking at light that has travelled for over 13 billion years to reach us. the galaxy we see duplicated in this image is not as it is today, but as it was in the universe's infancy. We are seeing a baby galaxy, a primordial building block of the cosmos, magnified and presented to us in exquisite detail thanks to this fluke of cosmic alignment. This is the central thesis of our journey. These rare and stunning phenomena, these cosmic mirages now captured with breathtaking clarity by the James Webb Space Telescope, are not mere optical tricks or celestial curiosities. They are unparalleled tools. They are keys that unlock multiple doors at once. They provide a unique laboratory to test the limits of Einstein's theory of general relativity under the most extreme conditions imaginable. They are our most powerful method for mapping the distribution of the enigmatic dark matter that constitutes the vast majority of the universe's mass. And they act as nature's own observatories, allowing us to peer deeper into the past than ever before, to witness the birth of the very first structures in the universe, the very first light after the Big Bang. This single mystifying image of a duplicated galaxy is therefore not an endpoint. It is a beginning. It is an invitation to an extraordinary detective story written in the language of bent light and warped time. It forces us to ask new and more profound questions. If we can use these lenses to map dark matter, can they also reveal something about the even more mysterious dark energy that is accelerating the expansion of the universe? If we are seeing multiple images of the same galaxy, does each image show us the galaxy at the exact same moment in time? The answer to that question will unravel our very notion of a single universal now. What was once a theoretical prediction, a bizarre consequence of a strange new theory of gravity, has now become our primary guide into the unknown. The universe's capacity for illusion has become our greatest instrument for discovery. As we stand before this cosmic mirage, we are like travelers in a desert who see a shimmering city on the horizon. We know it is not real in the way we expect, but we also know that the mirage itself is telling us something true and vital about the environment we are in. It is a signpost pointing the way toward a deeper understanding. The journey to deciphering this message has just begun. We must now step through the looking glass to follow the bent paths of light back to their source, back through the gravitational labyrinth of a galaxy cluster, back to the dawn of time itself to uncover the truths that lie hidden behind the most beautiful illusion in the cosmos. The puzzle is set, the tools are in our hands, and the secrets of the universe are waiting to be revealed within the ghostly echoes of a single impossibly duplicated galaxy. What if the most fundamental thing you trust about the universe, the very light that reaches your eyes from the farthest stars, is a magnificent liar? What if the cosmos is a grand hall of mirrors where the straight path is an illusion, and gravity itself conspires to create phantoms? We believe light travels in a straight line, an unwavering arrow shot from the past to the present. For centuries, this was the bedrock of our understanding, a principle so absolute it seemed woven into the definition of reality. Isaac Newton saw the universe as a grand, predictable machine, a celestial clockwork governed by an invisible force he called gravity. It was a simple, elegant pull, a direct attraction between any two masses, from an apple falling to the earth to the moon perpetually falling around it. His laws were perfect. They predicted the orbits of planets with breathtaking accuracy, charted the courses of comets, and gave humanity a sense of mastery over the heavens. Gravity in this majestic Newtonian cosmos was a force that acted across space. But it never occurred to anyone that it could act on space itself. Space was just the stage, the empty passive arena where the celestial ballet unfolded. Time, too, was an immutable river flowing forward at the same constant rate for everyone everywhere. It was a comfortable, comprehensible universe. And it was about to be shattered. In the early 20th century, a young patent clerk in Bern, Switzerland began to dream. Not of gears and levers, but of falling elevators and beams of light. Albert Einstein was wrestling with a profound contradiction, a deep crack in the foundation of physics. Newton's gravity was supposedly instantaneous, a force that could reach across the entire universe in a flash. Yet Einstein's own special theory of relativity, published a decade earlier, had established a cosmic speed limit. Nothing, not even information, could travel faster than light. How could gravity then be exempt from this universal law? This paradox gnawed at him, suggesting that our entire conception of gravity was fundamentally wrong. His journey into this mystery would not lead to a minor correction of Newton's work. It would lead to its complete demolition and the construction of something far more bizarre, more beautiful, and more powerful in its place. Over 10 years of relentless thought experiments of filling blackboards with equations only to erase them in frustration, Einstein arrived at a conclusion so radical it bordered on the absurd. He proposed that gravity was not a force at all. It was a consequence, a side effect of the geometry of the universe itself. He asked us to imagine that space and time are not separate and absolute, but are fused together into a single four-dimensional continuum spacetime. This is the true fabric of the cosmos, and this fabric, he declared, is not rigid and unchanging. It is dynamic, flexible, almost alive. The presence of mass and energy does not simply exert a pull through this fabric. It warps it, curves it, dents it, just as a heavy bowling ball sinks into the surface of a stretched rubber sheet. The sun does not pull the Earth with an invisible tether. Instead, the colossal mass of the sun creates a profound depression in space-time, a gravitational valley. The Earth in its orbit is not being yanked around. It is simply following the straightest possible path through that curved, distorted geometry. It is rolling along the rim of the valley created by the sun. This was the heart of his general theory of relativity, a revolutionary vision that transformed the universe from a static stage into a dynamic flowing ocean where planets, stars, and even galaxies are just buoys bobbing on its currents. But this spectacular new idea came with an even more mind-bending prediction. If massive objects could warp space-time, then anything travelling through that space-time must follow its curves, and that included the one thing thought to be immutable, the one thing that was supposed to define a straight line, a beam of light. Einstein predicted that light from a distant star passing close to a massive object like our own sun would not travel straight. Its path would be bent deflected by the sun's gravitational valley. The star would appear to us to be in a slightly different position in the sky than it actually was. It was a ghost image, a celestial sleight of hand performed by gravity. The effect would be minuscule, a deflection so tiny it would be utterly impossible to measure under normal circumstances, as the sun's own brilliant glare would completely wash out the faint light of any background star. There was, however, one fleeting opportunity to test this outrageous claim: a total solar eclipse. For a few precious shadowy minutes, when the moon perfectly blocked the sun's face, the sky would darken enough for the stars near the solar limb to become visible. An astronomer could photograph that star field during the eclipse, and then months later photograph the same star field at night when the sun was far away. If Einstein was right, the positions of the stars in the eclipse photograph, the ones whose light had grazed the sun, would be subtly shifted. It was a direct, unambiguous test. A chance to prove whether the universe was Newton's clockwork or Einstein's warped tapestry. The scientific establishment was deeply skeptical. The idea that space itself could be bent seemed like a fanciful fiction, and many saw Einstein as a brilliant but perhaps unmoored theorist. But for one man, the English astronomer and Quaker Sir Arthur Eddington, it was a challenge that had to be met. The year was 1919. The world was just emerging from the brutal shadow of the Great War, a conflict that had shattered empires and pitted nations, including Britain and Germany, against each other in unimaginable slaughter. In this climate of bitter division, Eddington saw an opportunity for science to heal, to demonstrate a shared human quest for truth that transcended national hatred. He would lead an expedition to observe the solar eclipse of May 29, 1919, a particularly long eclipse with the sun conveniently positioned in front of a rich cluster of stars called the Hyades. It was the perfect natural laboratory, but the mission was a monumental gamble. Two teams were dispatched to opposite sides of the Atlantic to double their chances of clear skies. Eddington himself sailed to the small island of Principe off the coast of West Africa, while a second team journeyed to Sobral in the north of Brazil. They carried heavy, delicate photographic plates and cumbersome telescope equipment on a voyage fraught with uncertainty. When the day of the eclipse arrived on Principe, the weather was conspiring against them. A torrential rainstorm had lashed the island all morning, and as the moment of totality approached, the sky remained stubbornly covered in thick clouds. For Eddington, it must have been agony. After months of planning, after travelling thousands of miles, the entire enterprise rested on a break in the weather that might never come. Then a miracle. Just as the moon began to fully obscure the sun, the clouds thinned. Patches of clear sky appeared, offering fleeting glimpses of the sun's ethereal corona and the faint pinpricks of light from the stars beyond. Working frantically, Eddington and his assistant managed to capture 16 photographic plates during the few minutes of darkness. Most were ruined by the cloud cover, but a precious few seemed to show the stars he was looking for. He had no way of knowing if he had succeeded. The subtle shift he was trying to measure was less than 2 arc-seconds in angle, equivalent to the width of a human hair seen from 70 feet away, proving it would require weeks of painstaking analysis back in England. Meanwhile, in Sobral, Brazil, the other team had much better luck with the weather obtaining a series of crystal-clear plates. The long journey home was filled with suspense. When Eddington finally developed his plates and began the meticulous process of measuring the positions of the stars, he looked for one tiny crucial displacement. He compared the eclipse plates to the reference plates of the same starfield taken months earlier, and there it was. Staring back at him from the glass negatives was the proof. The stars were not where they were supposed to be. Their light had been bent by the sun's gravity, and by an amount that matched not the old Newtonian prediction, but Einstein's radical new one almost perfectly. On November 6, 1919, at a packed joint meeting of the Royal Society and the Royal Astronomical Society in London, the results were announced. The universe was not as we had known it. Spacetime was real, and it was curved. The announcement made headlines around the world. Albert Einstein overnight became a global icon, the embodiment of scientific genius. His theory, once seen as a strange abstraction, was now a confirmed physical reality. The confirmation was a landmark moment, but the practical implications of light bending seemed at the time to be little more than a celestial curiosity. Einstein himself, in a 1936 paper, calculated the chances of ever observing the light from one star being bent by another star, creating a perfect ring-like image. He dismissed the possibility, concluding the effect was too small, and the alignment required too precise to ever be seen. The idea of using this phenomenon as a tool, as a form of cosmic telescope, was relegated to the fringes of astronomy. It was the brilliant and often eccentric Swiss-American astronomer Fritz Zwicky who just a year later fiercely countered this pessimistic view. Zwicky, a man famous for his abrasive personality and his visionary ideas, recognized the true potential of what he termed gravitational lensing. He reasoned that while the effect between individual stars might be negligible, the effect produced by an entire galaxy would be immense. Zwicky correctly predicted that a massive galaxy, or even a cluster of galaxies, could act as a colossal gravitational lens. He argued that these lenses would be powerful enough not only to bend the light from a more distant object, but to magnify it, to brighten it, making it possible for us to see things that would otherwise be too faint and too far away. He even suggested that these cosmic telescopes could be used to measure the mass of the lensing galaxies, and by extension weigh the universe itself. His ideas, published in the 1930s, were largely ignored. They were seen as wildly speculative, and the technology to detect such an effect simply didn't exist. For over 40 years, the concept of gravitational lensing lay dormant, a theoretical jewel, buried in obscure academic journals. The universe kept its secrets, and astronomers continued to peer into the dark with conventional telescopes capturing light that they still assumed, for all practical purposes, travelled in a straight line. The revolution that began with Eddington's eclipse plates had stalled. It took until 1979 for technology and luck to finally catch up with Zwicky's vision. While observing a distant, powerful object known as a quasar, astronomers Dennis Walsh, Bob Carswell, and Ray Wayman were puzzled by what they saw. Their instruments registered not one quasar, but two sitting side by side in the sky. They were identical twins. They had the exact same brightness, the same colour, the same spectral fingerprint, a unique barcode of light that identified them as originating from the same source. The odds of two completely different quasars being so perfectly matched were astronomically small. The team realised they were not looking at two separate objects at all. They were seeing a single distant quasar whose light had embarked on an epic journey across billions of light years. On its way to us, that light had passed through the gravitational field of a massive unseen galaxy, positioned directly in our line of sight. That foreground galaxy, the lens had split the quasar's light, bending it along two different paths through its warped spacetime. The two paths then converged back at our telescopes on Earth, creating a double image of a single object. It was a cosmic mirage, a phantom echo created by gravity's curve. This discovery, the twin quasar, was the first definitive observation of a gravitational lens, and it opened the floodgates. The phenomenon was not just a theoretical curiosity, it was real and it was observable. Suddenly astronomers were looking at the sky with new eyes, actively hunting for these gravitational illusions, and what they began to find was stranger and more spectacular than they could have imagined. Just a few years later, they found a different configuration, an even more stunning testament to Einstein's theory. It became known as the Einstein Cross. At its heart lies a relatively nearby galaxy, its diffuse light forming a hazy core. But perfectly centered on this galaxy, arranged in a breathtakingly symmetrical cruciform pattern, are four brilliant blue points of light. Those 4 points are not stars within the foreground galaxy. They are 4 distinct images of a single, much more distant quasar located billions of light years directly behind it. The light from that quasar has been warped and quadruplicated by the gravitational field of the intervening galaxy, a cosmic funhouse mirror, creating a phantom cloverleaf in the sky. The Einstein Cross was more than just a beautiful anomaly. It was a Rosetta Stone for understanding the nature of these lenses. The precise positioning and brightness of the 4 images allowed astronomers to build detailed maps of the lensing galaxy's gravitational field. In doing so, they could calculate its total mass. And this led to a startling revelation. The mass required to produce the lensing effect they were seeing was far, far greater than the mass of all the visible stars, gas and dust in the galaxy combined. The lens was being powered by something they couldn't see. Something invisible, mysterious and profoundly massive. It was one of the first most powerful pieces of evidence for the existence of dark matter, the unseen scaffolding upon which our universe is built. Gravitational lenses were no longer just confirming Einstein's theory. They were revealing a cosmos that was 95% hidden from our view. Throughout the late 20th century, with the help of the Hubble Space Telescope and powerful ground-based observatories, our catalogue of these cosmic mirages grew. We found not just multiple images, but elegant sweeping arcs of light, the smeared-out images of distant galaxies stretched and distorted into crescents by the gravity of massive galaxy clusters. In cases of near-perfect alignment, we saw the ultimate prize Einstein thought impossible: complete circles of light, ethereal halos known as Einstein rings. Each discovery was a triumph, a validation of a theory born in a patent office nearly a century earlier. But each observation was also incredibly difficult. These lenses are faint. The distortions are often subtle. Earth's own turbulent atmosphere blurs the images, smudging the fine details and making the most delicate arcs impossible to resolve. Even Hubble, floating high above the atmosphere, was limited. It was designed to see the universe primarily in visible and ultraviolet light. The most ancient, most distant galaxies, the very ones whose light would be most magnified by these lenses, have had their light stretched by the expansion of the universe itself, shifting it far into the infrared part of the spectrum, a wavelength of light to which Hubble was mostly blind. We could see the phantoms, but we couldn't see the ancient ghosts behind them. We were like detectives at a crime scene, able to see the distorted reflections in a shattered mirror, but unable to see the person casting them. To push deeper, to truly harness the power of these natural telescopes and gaze back toward the dawn of time, we needed a new kind of eye. An eye that could see the invisible infrared universe with unprecedented clarity. We needed a machine that could capture the faint, stretched-out light from the very first galaxies using gravity's own lens to reveal the secrets of cosmic dawn. The stage was set, the theory proven, the tantalizing clues gathered. But the greatest revelations were still waiting, hidden in the dark, waiting for a golden eye to open and stare back into the beginning. And so, after generations of peering into the gloom, we had reached a wall of dust and a wall of time. Our greatest instruments, paragons of human ingenuity, could push no further. The earliest flickers of cosmic dawn remained tantalizingly out of reach, their light stretched by cosmic expansion into a ghostly glow a wavelength our eyes, and even Hubble's, were never designed to see. To breach that final barrier to witness the universe's very first chapter, we would need more than a better telescope. We required an entirely new kind of sense, a machine tuned not to the brilliant light of the present, but to the ancient thermal whispers of the past. We needed a new eye in the sky, and we would send it 1,000,000 miles from home to a place of perfect cold and darkness. This new eye is the James Webb Space Telescope, a colossal origami of gold and gossamer unfolding itself in the void like some impossible clockwork insect. Its primary mirror a breathtaking honeycomb of 18 beryllium hexagons, each polished to a nearly flawless sheen and coated in a microscopically thin layer of pure gold, was designed for a singular audacious purpose. Gold is the perfect reflector of infrared light, the very essence of the ancient universe we sought. This was not a mirror built for vanity. It was a net exquisitely crafted to catch the faintest, oldest photons in existence. Stationed at the second Lagrange point, a point of gravitational stability where it could orbit the Sun in lockstep with the Earth, JWST uses a 5-layer sun shield the size of a tennis court to block the light and heat from our own solar system. This shield cools the telescope's instruments to a staggering 233 degrees below 0 Celsius, a temperature so close to absolute zero that the telescope's own thermal glow becomes negligible. Only in this profound manufactured cold can it become sensitive enough to register the feeble warmth of a galaxy, burning 13 billion light-years away. This is the first of its revolutionary powers, its infrared vision. Think of the universe as a vast ancient city, and its oldest, most foundational districts are shrouded in an impenetrable fog. This fog is cosmic dust, immense clouds of fine-grained particles ejected by dying stars, which absorb and scatter the visible light we are used to seeing. Hubble, for all its power, saw mainly the fog, but infrared light with its longer wavelength slips through this cosmic haze almost unhindered. For JWST, that dusty veil simply evaporates, revealing the brilliant star-forming nurseries and turbulent galactic cores that were previously hidden from view. But this is only half the story. The telescope's infrared sensitivity addresses a much more profound obstacle, the very expansion of spacetime itself. Just as the pitch of a siren lowers as it speeds away from you, the wavelength of light from a distant galaxy is stretched as the universe expands between us. This cosmic Doppler effect, this redshift pushes the brilliant ultraviolet and visible light emitted by the first stars so far down the spectrum that by the time it completes its 13 billion year journey to us, it arrives as the faint invisible warmth of infrared. JWST is therefore more than a telescope. It is a meticulously calibrated time machine tuned precisely to the frequency of creation. It is engineered to see ghosts. Its second power is its sheer scale and precision. That 6.5 meter golden mirror gives it a collecting area more than 6 times larger than Hubble's, allowing it to capture exponentially more of that precious ancient light. This grants it an unprecedented resolving power, the ability to discern fine detail at unimaginable distances. It is the difference between seeing a distant city as a vague smudge of light and being able to pick out the individual streetlights. This combination of sensitivity and resolution means JWST can do more than just detect the first galaxies. It can begin to dissect them to see their nascent structures, their first clumsy attempts at forming spiral arms, their central supermassive black holes just beginning to stir. It was with this arsenal of capabilities, this promise of a revolution in sight, that a team of astronomers pointed the telescope towards a seemingly unremarkable patch of the southern sky in the constellation Volans. Their program was called GLASS, the GRISM, Lens Amplified Survey from Space. Their goal was simple, yet among the most ambitious in all of science, to use the magnifying power of a massive galaxy cluster, a cosmic heavyweight named Abell 2744, as a natural telescope to find the faintest, most distant objects ever observed. The team was a global collaboration, a consortium of minds from institutions across the world, all united by this shared hunt. For months they had planned, simulated and debated. Now, all they could do was wait. The observation commands were sent hurtling across the million-mile gap to the telescope. JWST pivoted its immense structure, locking onto the coordinates with unwavering precision, and then for hours it simply stared. Its instruments NIRCam and NIRSpec, the near-infrared camera and spectrograph, drank in the light photon by precious photon, building an image of a depth and clarity previously confined to the realm of theory. The raw data began its long journey back to Earth, a torrent of binary code received by the massive dishes of the Deep Space Network. At the Space Telescope Science Institute in Baltimore, powerful computer systems hummed to life, translating this stream of ones and zeros. They stitched together exposures, calibrated the detectors, and subtracted instrumental noise, slowly, painstakingly coaxing a picture of the universe from the raw digital signal. For the scientists waiting, refreshing their screens from home offices and university labs around the globe, this was the moment of truth. Among them was Haojing Yan, an astronomer at the University of Missouri, and his team. As the first processed images from the GLASS survey became available, a collective sense of awe rippled through the community. The sheer number of galaxies in the frame was staggering. Every pinprick of light, every faint reddish smudge was an entire island universe, some nearby, some impossibly remote. The field was a core sample drilled through cosmic time. But as Yan and his colleagues began to meticulously scan the image, their trained eyes looking for the telltale signatures of extremely distant, highly redshifted galaxies, something else caught their attention. It was subtle at first, an almost trivial peculiarity in a field crowded with wonders. In one corner of the frame, nestled among the distorted arcs and smears created by the Abell 2744 cluster, were two objects. They were small, compact, and distinctly red. This alone was not unusual. The field was full of red objects. What was deeply strange, what made the astronomers lean closer to their screens, was that these two objects looked identical. It was more than just a passing resemblance. They shared the same shape, a slightly elongated oval. They shared the same brightness. And crucially, when the team began to analyze their light, they shared the exact same color profile across JWST's multiple infrared filters. This was the astronomical equivalent of finding a perfect, unexplainable duplicate of a single unique fingerprint at two different crime scenes. The scientific mind is trained for skepticism, and the immediate assumption was that this had to be an error. The telescope was new, its systems still being commissioned and understood. The first suspect was an instrumental artifact, a ghost in the machine. Perhaps a cosmic ray had struck the detector in a peculiar way, creating a false echo. Or maybe it was a glitch in the complex software pipeline that assembled the final images, a digital hiccup that had copied and pasted a small patch of pixels. The team went to work with a methodical, almost prosecutorial zeal, determined to debunk their own potential discovery. They pulled the raw, uncolour-vibrated data frames, looking at the exposure before any software had touched it. The duplicate was still there. They checked the data from different exposures taken at slightly different times with a telescope dithered, moved by a minuscule amount to help identify and remove just such artifacts. The duplicate remained stubbornly fixed in its celestial position, relative to all the other galaxies. It was not a glitch, it was real. The next hypothesis was that they were two distinct but remarkably similar galaxies that just happened to be near each other. Perhaps a pair of interacting dwarf galaxies, their gravitational dance triggering a burst of star formation that made them look alike. This was a plausible, if less exciting, explanation. To test it, they needed a spectrum. They had to capture the light from the objects and spread it out into its constituent colours, a rainbow that holds the chemical fingerprint of the galaxy, and most importantly, a precise measurement of its redshift, its distance. Using JWST's near-infrared spectrograph, they targeted the pair. The result was the final definitive clue that shattered the conventional explanations. The spectra were not just similar, they were identical. Every emission line, every subtle absorption feature was perfectly mirrored. The redshift was the same for both, and it was enormous, placing them at a staggering distance, their light having travelled for nearly 13.5 billion years. They hailed from an era when the universe was less than 400 million years old, a mere toddler in cosmic terms. The probability of two separate galaxies in the chaotic environment of the early universe, evolving in such a perfect parallel fashion to have identical structures and identical stellar populations, was effectively zero. The team was left with only one conclusion, an explanation that was once the realm of science fiction, but was now staring back at them from their data. They were not looking at two galaxies, they were looking at one. They had found their Cosmic Mirage. The massive foreground cluster Abell 2744, a colossal aggregation of galaxies' gas and unseen dark matter, was acting as a gravitational lens. Its immense mass, trillions of times that of our Sun, was warping the very geometry of spacetime around it. Just as a glass lens can bend and focus light, this cosmic behemoth was bending the path of light from the universe behind it. The light from a single distant background galaxy had travelled towards us on a path that took it right through the cluster's powerful gravitational field. Some of that light was diverted one way, some another, its path split by the complex lumpy distribution of matter in the cluster. These two separate light paths, after being bent and magnified, then continued their journey across the cosmos, finally arriving at JWST's golden mirror at the same moment, but from slightly different directions. The telescope, unaware of this celestial sleight of hand, simply recorded what it saw: two identical images of the same galaxy projected onto the sky. To confirm this, the astronomers built a detailed model of the gravitational field of their Abell 2744 cluster. Using the positions and distorted shapes of hundreds of other lensed galaxies in the image, they could map the invisible scaffolding of dark matter that dominated the cluster's mass. They were in effect calculating the precise curvature of space-time across the entire field of view. When they ran their simulations, the result was breathtaking. Their model predicted that a galaxy located in the far distant background at that precise redshift would have its light split and magnified, producing multiple images, and the predicted locations of the two brightest of these images fell exactly where the team had observed the mysterious duplicates. It was the final triumphant confirmation. The puzzle was solved. The awe that had been building within the team finally gave way to a profound sense of discovery. This wasn't just a clever trick of gravity, it was a gift from the universe. Gravitational lensing had not only created this startling duplicate, but had also magnified it immensely, making it appear many times brighter than it otherwise would. They had been handed a cosmic microscope focused on a single isolated subject from the era of cosmic dawn. This single galaxy, now nicknamed Sparky, was suddenly accessible to us in a way that should have been impossible. We could study its chemistry, measure its rate of star birth, and scrutinize its structure, all thanks to this fluke of cosmic alignment. This was not just another data point, it was a portal. The James Webb Space Telescope had been operational for only a few weeks, and it had already delivered a postcard from a time and place we had only ever dreamed of visiting. The discovery of this cosmic mirage was more than just a success for the glass team. It was a declaration. A new era of seeing had begun. We now had an eye that could not only pierce the veil of dust and time, but could also leverage the universe itself as an instrument revealing secrets that had been hidden since the beginning of all things. And this was just the first whisper from the abyss. The real question, the one that now hung in the air with electric potential, was what story this ghostly echo from the past was waiting to tell us, undefined. And so, the impossible image burns itself into our consciousness. Not a glitch in the telescope's hardware, not an error in the data stream, but a genuine repeating pattern in the fabric of the cosmos. The question that has echoed through the halls of astronomy for months finally demands an answer, and it is an answer that resides not in the duplication of matter, but in the very nature of reality itself. The solution to this cosmic riddle has nothing to do with phantom galaxies or strange celestial biology giving birth to identical twins. Instead, it lies within a profound and elegant truth about the universe, a secret whispered by Albert Einstein over a century ago, that space is not a void and time is not just a clock. They are a single, unified entity, space-time, a dynamic, pliable fabric that can be stretched, compressed, and most importantly warped. What we are witnessing in this breathtaking photograph from the Webb is not a case of cosmic duplication, but a grand illusion. We are looking at a mirage crafted on a scale so immense that it defies all terrestrial comparison, a trick of light and gravity that transforms the universe into a colossal funhouse mirror. To understand this celestial sleight of hand, you must first forget what your eyes tell you about the emptiness between the stars. Imagine that you could drain the universe of all its light, leaving only the anchor of its gravity, its invisible architecture. In that profound darkness, you would see the true monster responsible for this spectacular deception. It is the colossal galaxy cluster looming in the foreground, a gravitational titan positioned perfectly between us and its distant victim. This is not merely a city of stars. It is a sprawling empire of mass. Thousands of galaxies, each containing hundreds of billions of suns, are bound together in an intricate, eternal gravitational dance. They swirl around a common centre of gravity, a point of such density that it has become a maelstrom in the placid ocean of space-time. Yet the light from these thousands of galaxies, the visible matter that we can count and catalogue, is a pittance. It accounts for only a fraction of the cluster's true gravitational might. The overwhelming majority of its mass, perhaps 85% of it, is something else entirely, an unseen, untouchable substance we have come to call dark matter. This is the cluster's ghost in the machine, its invisible skeleton. We cannot see it. We cannot capture it. We cannot directly measure it, but we can feel its presence with absolute certainty. We feel it in the impossibly high speeds of the outer galaxies, which are being whipped around the cluster's core so fast they should by all rights be flung out into the intergalactic void. Something is holding them in place, an immense gravitational glue that permeates the entire structure, and it is this dark matter that elevates the cluster from a simple galactic metropolis into a cosmic super-predator of gravity. Together, the visible and the invisible conspire to create an object so profoundly massive it no longer sits in space-time. It fundamentally alters the geometry of space-time around it. Think of space-time as a vast, taut rubber sheet stretching to infinity. A single star would be like a small marble creating a tiny dimple. A galaxy a bowling ball creating a more significant depression. But this cluster, this is something else. It is like placing a singularity, a mountain of neutron stars, onto the very centre of the sheet. The fabric groans under the strain, warping catastrophically, creating a deep, wide, inescapable gravitational well. This distortion is not just a local phenomenon. Its influence radiates outwards for millions of light years in every direction, a silent, invisible testament to its unimaginable mass. And it is this profound warping, this deep valley in the cosmos, that serves as our lens. Now picture the light from that single, distant background galaxy, the true subject of our story, born in the universe's infancy. Its photons began their journey across the cosmos billions of years ago, travelling in what they perceived to be a perfectly straight line, an unwavering arrow shot from the bow of cosmic history. For eons, their path was largely uneventful, a lonely pilgrimage through the expanding, darkening void between galactic filaments. But then, as they approached the midway point of their journey to us, they encountered this unforeseen obstacle, the warped domain of the Great Cluster, this gravitational mountain range in their path. Light, for all its incredible speed, is not immune to gravity. Einstein's genius was in realizing that light follows the straightest possible path there through space-time. But if space-time itself is curved, then the path of light must also curve. It has no other choice. And so the stream of photons from our ancient galaxy, which had travelled for so long as a single unified wavefront, was forced to make a decision. It encountered the gravitational slope of the cluster and it split. Imagine a river flowing steadily through a flat plain, only to meet a massive smooth boulder rising from the earth. The water does not stop. It parts, flowing around the obstacle on all sides, some of it streaming over the left flank, some over the right, before eventually converging once more on the other side. This is precisely what happened to the light from our galaxy. As the photons plunged into the cluster's gravity well, their paths were bent, their trajectories irrevocably altered. One stream of light was deflected on a path that took it high, above the densest part of the cluster's core. Another stream was bent on a different course, one that swung low underneath that same gravitational nexus, and it's possible, even probable, that other streams of light were diverted on even more complex pathways, snaking around individual massive galaxies within the cluster itself. Each of these paths represented a different journey through the cosmos, a distinct route carved through the warped geometry of space-time. Crucially, these different paths were not of equal length. The light that took the higher, wider arc around the cluster's core had to travel a slightly longer distance than the light that took a more direct, though still curved, path. The difference might be minuscule on a cosmic scale, a few light weeks or light months over a journey of billions of years, but it is a difference that has staggering consequences. It means that the light from these different paths did not arrive at our telescope, the James Webb, at the same time. The photons that took the shorter journey arrived first. The photons that took the slightly longer path arrived later, perhaps days, months, or even years behind their brethren. Think about that for a moment. We are not just seeing the same galaxy from different angles, we are seeing the same galaxy at slightly different moments in its life. If a star in that galaxy were to explode as a supernova, we would see the cataclysmic event happen first in one image. Then, after waiting for the light to complete its longer journey, we would witness the exact same star explode a second time in the second image, a ghostly delayed replay of a cosmic death, a message with a time delay written into the structure of the universe. This temporal echo is the key to understanding the mirage. Our telescope, perched in its stable orbit 1 million miles from Earth, is the downstream point where these divergent rivers of light finally reconverge after their long and separate journeys. Billions of years after being split apart by the immense gravity of the foreground cluster, these distinct streams of photons all come flooding into the primary mirror of the James Webb Space Telescope. Because they are arriving from slightly different apparent directions on the sky, the telescope's sophisticated optics resolve them not as one overlapping source, but as separate distinct points of light. One image is formed by the light that took the upper path. The other seemingly identical image is formed by the light that took the lower path. What appears to our eyes as a duplicate cosmic twin is in truth a time-delayed ghost, an echo of light from the same source, its image displaced and reformed by the gravitational lens. This phenomenon, known as strong gravitational lensing, is one of the most powerful and beautiful predictions of general relativity. And it doesn't just create duplicate images. The precise appearance of the lensed galaxy depends with exquisite sensitivity on the alignment between us, the lensing cluster, and the background source galaxy. If the alignment is just slightly imperfect, the background galaxy's light isn't focused into clean separate images. Instead, the tidal forces of the gravity well stretch and distort it, smearing its light into magnificent luminous arcs. We have seen these celestial brushstrokes in other JWST images, glowing crescents of impossible length and thinness, often wrapping partially around the very galaxies that are bending their light. Each arc is the distorted image of a single normal galaxy, its form tortured and magnified into a thing of ethereal beauty, a gravitational signature painted across the black canvas of the void. These arcs are a map of the invisible, tracing the precise curvature of spacetime created by the lens. By studying their shape, their curvature, and their brightness, we can actually reconstruct the distribution of the unseen dark matter in the foreground cluster, using the distorted light as our guide. But there is an even more perfect, more sublime configuration. It is the holy grail of gravitational lensing, an alignment so rare it borders on the miraculous. When the background source galaxy, the very centre of mass of the lensing cluster, and our telescope on Earth all fall into a single perfectly straight line across billions of light years, something extraordinary happens. The light from the background galaxy is no longer split into two images or stretched into an arc. Instead, it is smeared into a complete, unbroken, perfect circle of light, a celestial halo surrounding the foreground lens. This is the Einstein ring, the ultimate proof of the theory. It is the universe drawing a circle to prove a point, a cosmic bullseye demonstrating that a single point of light has been wrapped completely around a massive object. Seeing an Einstein ring is like finding a flawless diamond on a beach of infinite sand. It is a consequence of an alignment so precise that the odds against it are quite literally astronomical. Yet for all the breathtaking beauty of these cosmic mirages, the duplicate images, the sweeping arcs, the perfect rings, their visual splendour is not the most profound part of the story. The true power of this phenomenon is not that it bends light, but that it magnifies it. The immense gravity of the foreground cluster acts as a lens in every sense of the word. Just as a magnifying glass uses a curved piece of glass to gather and focus the light from a tiny object, To make it appear larger, this cluster uses its curved spacetime to gather and focus the faint light from a galaxy billions of light years away. It is a natural telescope forged not from glass and steel, but from dark matter and the gravity of 1,000 galaxies. It is a cosmic telescope with a lens millions of light years across, vastly more powerful than any instrument we could ever hope to construct. And it is this magnification that is the true gift of the Mirage. The distant galaxy we are seeing duplicated is not just any galaxy. Its light comes to us from the dawn of time, from an era when the universe was less than 1 billion years old, when the very first generations of stars were just igniting. Without the aid of this gravitational lens, this galaxy would be at the absolute limit of what even the James Webb could detect. It would appear as a faint red, unresolved smudge, its secrets locked away by immense distance and cosmic dimness. But the lens changes everything. By amplifying its light perhaps by a factor of 10, 20 or even 50, the Cosmic Mirage brings this infant galaxy into sharp focus. It transforms a blurry speck into a detailed portrait. Suddenly we can see structure within it. We can identify individual star-forming regions, brilliant blue knots of nascent stars, lighting up their natal cocoons of gas and dust. The duplication is not a cosmic error. It is a cosmic invitation. It is a rare, perfect alignment that has unlocked a door to the past, offering us an otherwise impossible, intimate glimpse into the universe's nursery, a chance to witness firsthand the chaotic and beautiful process of galaxy formation in its infancy. The illusion has revealed a deeper truth. Now that we understand the physics of the Mirage, a new set of questions comes rushing to the forefront, questions of even greater importance. What secrets does this magnified vision of the past hold? What can this ghostly echo from the beginning of time tell us about the origins of everything we see around us today? And so, we are left staring at a ghost, a celestial apparition duplicated and smeared across the velvet darkness by the unseen hand of gravity. The Cosmic Mirage is not a single entity, but a fractured echo, a message from the dawn of time that has been broken into pieces during its 13 billion year journey. But to understand this message, to read the secrets encoded within that ancient light, we cannot simply admire the beautiful distortion. We must first face the profound challenge it represents. These images, as stunning as they are lies. They are magnificent cosmic falsehoods warped by the very fabric of space-time they traversed. Each arc, each glowing knot of stars is a view through a flawed and impossibly complex lens. Imagine finding a precious shattered photograph from a lost civilization. You have several large pieces, but each one is bent, stretched and discoloured by heat and pressure. The true image is hidden within the damage. You couldn't possibly understand the culture that created it by studying the warps and burns. You must first meticulously, painstakingly reverse the damage to every single fragment. This is the monumental task facing astronomers. The lensed images of our distant galaxy are not clean copies. They are funhouse mirror reflections where straight lines become curves, circles become ellipses, and compact star clusters are stretched into incandescent streaks of light. The magnification isn't uniform. Parts of the galaxy are brightened by factors of 10, while others nearby are barely amplified at all. This differential magnification, this shearing and twisting, scrambles the galaxy's true nature. How can we measure the real size of its star-forming nurseries? How can we map the true distribution of its nascent spiral arms? We can't. Not from this broken picture. The light carries the intrinsic information, the galaxy's mass, its chemical composition, the speed of its rotation, but it's all been filtered through this gravitational labyrinth. The lens doesn't just create copies, it imposes its own signature, its own gravitational fingerprint over every photon. To reveal the pristine source, we must first build a perfect model of the lens itself. We have to map every contour, every peak and every valley in the gravitational landscape of the foreground cluster that is responsible for this grand illusion. It is an act of cosmic archaeology, in reverse, not digging down into the past, but computationally peeling back the layers of space-time itself. The process begins not with the Cosmic Mirage alone, but with everything around it. The James Webb Space Telescope stares unblinkingly at the lensing cluster, identifying dozens, sometimes hundreds of other fainter background galaxies, each one subtly distorted by the cluster's immense gravity. Every tiny stretched ellipse, every faint, barely perceptible arc becomes a crucial piece of data. Each one is a silent witness to the path light must travel through this region of space. These numerous, less dramatic lenses act as a web of constraints, tiny guideposts that reveal the shape of the invisible gravitational field. Scientists gather these distorted shapes and feed them into some of the most powerful supercomputers on Earth. Their task is to build a digital twin of the galaxy cluster, a simulation so precise it can replicate the universe's own handiwork. But this is where the true mystery deepens. When they begin to model the cluster, they immediately confront a ghost in the machine. The gravity of all the visible stars, all the glowing gas and dust in the foreground galaxies, isn't nearly enough. It accounts for perhaps 15% of the required gravitational pull. The rest, the overwhelming majority of the mass responsible for this spectacular mirage, is utterly and completely invisible. It is dark matter. The astronomers are forced to map a substance they cannot see, whose nature they do not understand, guided only by its gravitational shadow. They are charting the contours of an invisible mountain range by observing the way the wind of distant starlight bends around it. The computer models churn through countless iterations, placing clumps of this mysterious unseen matter throughout the digital cluster. Each simulation is a hypothesis. What if the dark matter is smoothly distributed? The model runs, generating a simulated sky. The astronomers then compare this digital sky to the real one captured by Webb. The lensed images don't match. The arcs are in the wrong place, the magnification incorrect. The hypothesis is wrong, so they try again. What if the dark matter is clumpy, concentrated around the largest galaxies? Another simulation runs, another comparison is made. Closer, but still no. The process is a relentless high-stakes search through a universe of possibilities. They tweak the mass of individual galaxies, adjust the distribution of the dark matter halos, and refine the geometry of the entire cluster over and over. They are sculptors chipping away at uncertainty, with algorithms and observations slowly carving out the true shape of this invisible cosmic behemoth. Days turn into weeks, weeks into months of computational effort. Millions of potential universes are born and die inside the silicon hearts of these machines. Each one is an attempt to solve gravity's grand equation, to find the one unique mass distribution that can perfectly explain the precise location, the exact shape, and the specific brightness of every single lensed image in the field of view. And then, after an astronomical number of calculations, it happens. A model converges, the simulated sky snaps into focus, and on the screen the computer-generated arcs and distorted galaxies are a near-perfect match for the reality Webb has shown us. They have done it. They have mapped the ghost. They have built a complete four-dimensional model of the lens, accounting for every gravitational dip and swell caused by both visible matter and its enigmatic dark counterpart. Now, and only now, can they perform the final magical act. With this perfect digital blueprint of the lens, they can computationally reverse the process. The software effectively takes the light from the distorted images of the Cosmic Mirage and traces its path backward through the simulated gravitational field. It undoes every twist, corrects for every stretch, and removes every iota of magnification. The light is guided back along its celestial detour, computationally lifted out of the gravity wells and sent back toward its origin. The funhouse mirror is digitally flattened, and as the program completes its run, something breathtaking appears on the screen. For the first time, human eyes can behold the distant galaxy as it truly is, or rather as it was 13 billion years ago. The fractured smeared light coalesces into a single pristine form. What we see is a revelation, a delicate compact spiral blazing with the violent blue light of furious star formation. We can see its central bulge, the clumpy chaotic nurseries where the first generations of stars are being born. We can measure its true size, its unadulterated brightness, and the speed of its rotation. A galaxy that was previously a scientific enigma, a beautiful but inscrutable smear, has been resurrected. Its secrets are finally laid bare, offering us an unprecedented window into the universe's turbulent youth. This single reconstructed image becomes a Rosetta Stone for understanding galaxy formation near the dawn of time. But this incredible feat of cosmic reconstruction as profound as it is only the beginning. The lens has a far deeper, more significant secret to tell, one that extends beyond the fate of a single galaxy and touches upon the destiny of the entire universe. A secret not of space, but of time itself. The multiple paths the light takes around the lensing cluster are not all the same length. Some photons travel a more direct route, while others are deflected on a much wider, more circuitous trajectory to reach our telescope. But there is another, even more mind-bending wrinkle born from Einstein's own theories. Gravity doesn't just bend the path of light, it warps the flow of time. A clock deep within a gravitational well ticks more slowly than a clock in emptier space. So the light from our distant galaxy that travels closer to the massive core of the lensing cluster is not only travelling a different distance, but it is also moving through a region where time itself is more sluggish. The consequence of these two effects, the path length difference and gravitational time dilation, is extraordinary. The light from the different images of the Cosmic Mirage does not arrive at Earth at the same time. It is a true cosmic echo, but an echo of light separated by years. Imagine you are standing in a vast canyon and you fire a starting pistol. The sound travels directly to a listener on the other side, but another copy of the sound bounces off a distant canyon wall travelling a longer path and arrives a few seconds later. The duplicate images of our lensed galaxy behave in exactly the same way. An event that happens in the distant galaxy, a star exploding as a brilliant supernova for example, will not appear in all the lensed images simultaneously. We will see the supernova flash in the first image to arrive. Then we must wait. Days, weeks, months, or in some cases over a year later, the light from that same explosion, having taken a longer and more time-dilated path, will finally arrive in the second image, then later still in the third. This phenomenon, called the gravitational lens time delay, transforms the Cosmic Mirage from a static photograph into a dynamic celestial clockwork. It provides a stunning confirmation of our understanding of gravity, but its true power is as a measuring tool of unimaginable scale. The length of the delay, the time gap between the supernova flashes, is exquisitely sensitive to two key factors: the precise mass distribution of the lensing cluster, which we have already painstakingly modelled, and the absolute physical distances involved in the entire system. If we know the lens model, and we can measure the time delay, we can calculate the distance from Earth to the lens, and from the lens to the background galaxy, with a precision that rivals and sometimes even exceeds our most trusted methods. The universe has provided us with a new cosmic yardstick. And why is this so critically important? Because measuring distances across the cosmos with high accuracy is the holy grail of modern cosmology. It is the key to understanding the expansion, the evolution, and the ultimate fate of our universe. For decades, cosmology has been facing a growing crisis, a deep and unsettling disagreement known as the Hubble tension. Measurements of the universe's current expansion rate, a value called the Hubble constant, give different answers depending on how they're made. Methods that look at the early universe, like the cosmic microwave background, predict one value. Methods that look at the local modern universe using standard candles, like supernovae and Cepheid variable stars, yield a consistently higher value. It's as if we measured a person's height as a child and predicted they'd be 6 feet tall, but when we measure them as an adult, they stand 6'5". Something is wrong. Something is missing in our cosmic model. This is where the Cosmic Mirage enters the grand stage. The time delay method provides a completely independent third way to measure the Hubble constant, a powerful referee in this cosmic debate. It relies on nothing but gravity and the speed of light, bypassing the complex stellar physics that underpins other techniques. Every lensed system with a measurable time delay becomes another crucial data point, another chance to zero in on the true expansion rate of our universe. When we see a flicker in one image of a distant lensed quasar, telescopes across the globe settle in for a long vigil, monitoring the other images, waiting for the echo. The tension is palpable. When the second image finally brightens right on schedule, as predicted by the model, it is a moment of profound triumph. The time delay is measured, the distances are calculated, and another pin is placed on the map of cosmic expansion. These measurements are already beginning to reshape our understanding, providing results that favour the higher value for the Hubble constant, deepening the mystery of the cosmic discrepancy. But the true potential is even grander. By studying many such lenses at different distances, we can do more than just measure the expansion rate today. We can map the expansion history of the universe across billions of years. We can see how the cosmic acceleration has changed over time, and in doing so, we gain our most direct insight into the very thing driving that acceleration, the enigmatic, all-pervading force we call dark energy. That beautiful, distorted mirage, first seen as a curiosity, has become one of our most powerful probes into the darkest and most fundamental secret of the cosmos. The light from a single faraway galaxy, bent and broken by a gravitational lens, carries within its echoes the story of cosmic destiny, a story that is only now, thanks to these celestial tricks of light and time, beginning to be told. And so the grand illusion becomes our most profound instrument. This cosmic sleight of hand, this trick of gravity and light, is not merely a curiosity for us to marvel at. It is a key one offered up by the universe itself to unlock its most fiercely guarded secrets. The very fabric of space-time, warped and curved by the colossal gravity of a galactic cluster, has now become our lens. It is a telescope of unimaginable power, one we could never hope to build ourselves, and with the James Webb Space Telescope acting as its eyepiece, we have brought its focus to bear on the edge of time. For decades, the most distant galaxies we could glimpse were little more than faint reddish smudges of amorphous light. They were whispers from a past so remote they seemed almost mythological, the faintest of embers from the cosmic dawn. We knew they were there, but their true nature, their internal anatomy, their soul remained shrouded in distance and shadow. We were like cartographers trying to map a continent from a single blurry photograph taken from orbit. We could see the general shape, but the mountains, the rivers, the cities, the very details that give a world its character were lost to us. This was the fundamental barrier, the Great Wall in our exploration of the early universe. To understand how we got here, how our own Milky Way was born, we needed to see its ancestors not as ghostly silhouettes, but as living, breathing entities. We needed to walk their streets. With this gravitational gift, the Webb telescope now does precisely that. The stretching and magnifying of the light is not uniform. It is a complex amplification that in some fortunate alignments can increase the apparent size and brightness of a background galaxy by a factor of 1050 or even 1000. Suddenly, the impenetrable wall of distance crumbles. What was once a single unresolved pixel of data now blossoms across Webb's infrared detector, unfurling into a stunning, intricate tapestry. You're no longer looking at a mere smudge. You're gazing into the heart of a nascent galaxy, a stellar metropolis under construction less than 500 million years after the Big Bang. The power of this cosmic conjunction is difficult to overstate. It is the astronomical equivalent of discovering a perfectly preserved ancient manuscript that not only describes a lost civilization, but also contains detailed blueprints of its cities and portraits of its citizens. Through Webb's golden eye, we can now resolve distinct brilliant knots of light within these primordial systems. These are not individual stars, not yet, but colossal nurseries, gargantuan clouds of hydrogen and helium collapsing under their own gravity to form the very first generations of star clusters. We see them as brilliant blue-white beacons churning cauldrons of creation, where thousands or even tens of thousands of stars are being forged in a single, violent burst of activity. Our elegant models of galaxy formation, built over decades of painstaking theory and indirect observation, often depicted this era as a time of smooth, orderly growth. We imagined vast serene disks of gas slowly coalescing, gracefully spiraling into the majestic structures we see in the local universe today. The lensed images from Webb shatter this placid picture. The infant galaxies we are now witnessing are nothing like the grand spirals that populate our cosmic neighbourhood. They are chaotic, clumpy, and spectacularly messy. They are not serene disks, but turbulent, irregular firestorms assembled from a series of violent mergers and collisions. We can see distinct streams of gas being pulled in from the cosmic web feeding the central furnace. We can identify multiple dense cores, the wreckage of smaller proto-galaxies being cannibalized to build a larger whole. This is not gentle formation. This is galactic embryology at its most ferocious and raw. We're watching the universe assemble itself piece by bloody piece. Each magnified image becomes a frame in the story of cosmic evolution. showing us that our own galaxy's placid spiral arms were born from a far more violent and tumultuous youth than we ever dared to imagine. This is not just a refinement of our theories, it is a fundamental rewriting of the opening chapters of galactic history, all thanks to a mirage. But the revelations extend far beyond the structure of these early galaxies. They reach back into one of the most mysterious and pivotal epochs in the history of the entire cosmos, the era of reionization. After the Big Bang, the universe cooled, and for hundreds of millions of years it was filled with a thick neutral hydrogen fog that made it opaque to ultraviolet light. This was the cosmic dark age. Then something happened. Some immense source of energy emerged, acting like a celestial blowtorch, and began to burn away this fog. It ionized the hydrogen-stripping electrons from their protons, and rendering the universe transparent as it is today. For decades, the prime suspect for this cosmic transformation was the intense radiation pouring from the first stars and galaxies. It was a beautiful theory, but one that was impossible to prove directly. We simply couldn't see those first galaxies clearly enough to measure if they were producing enough ionizing photons, or if those photons could even escape their host galaxies to do the work. It was a cosmic cold case with no eyewitnesses. The lensed galaxies seen by Webb are those eyewitnesses, because the lensing effect magnifies not just the galaxy's light, but its entire spectrum. We can perform an unprecedented cosmic autopsy. Webb's spectrographs can slice the magnified light into its constituent wavelengths, creating a chemical barcode that tells us exactly what is happening inside these stellar nurseries. For the first time, we are directly measuring the torrent of high-energy ultraviolet photons blasting out from these young, massive, incredibly hot stars. The data streams back to Earth, and the story it tells is breathtaking. We can see that these early galaxies were far more efficient at this process than their modern counterparts. Their chemical makeup was more primitive, their stars burned hotter and brighter, and their structures were porous enough to allow this fierce radiation to escape into the intergalactic medium. In these magnified images, you can almost see the bubbles of transparency being carved out of the primordial fog. We're no longer speculating about the end of the cosmic dark ages. Through nature's own telescope, we are witnessing the very engines of reionization in action. We are watching the sunrise of the modern universe, a dawn that took place 13 billion years ago, its light stretched and guided to our telescope by a cosmic mirage. It is a discovery that closes a fundamental chapter in the story of creation, finally confirming how the cosmos became the transparent light-filled expanse we know today. Yet this extraordinary tool has a dual function. While it uses a foreground object to magnify a background one, it simultaneously allows us to dissect the lens itself with a precision that borders on science fiction. The lensing galaxy cluster, that colossal congregation of hundreds or thousands of galaxies, is dominated not by the stars we can see, but by an invisible substance that outweighs everything else by a factor of 5 dark matter. This mysterious, unseen material forms the gravitational backbone of the universe. It is the invisible scaffolding upon which all visible structures are built. We know it exists because of its gravitational influence. It is the phantom limb of the cosmos felt, but never seen. For decades, mapping its distribution has been a painstaking indirect process, relying on the subtle statistical warping of thousands of background galaxies, a technique known as weak lensing. It gave us a blurry, low-resolution picture, like trying to infer the shape of a mountain by observing the way wind flows around it. Strong gravitational lensing, the very phenomenon creating these dramatic mirages, changes the game entirely. Each duplicated, warped and stretched image of the distant galaxy is a precise gravitational probe. Its exact position, its shape and its brightness are dictated by the precise path its light took through the lensing cluster. It is a problem of reverse engineering on a cosmic scale. If we know where the images appear and what they look like, we can reconstruct the gravitational landscape that must exist between them and us to create that specific pattern. Astronomers become cosmic cartographers, using the lensed images as survey markers to draw a topographical map of gravity itself. With the razor-sharp clarity of the James Webb Space Telescope, we can pinpoint the positions of these multiple images with astonishing accuracy. This allows us to create the most detailed and high-resolution maps of dark matter ever conceived. We are no longer inferring the mountain's shape from the wind. We are charting every peak, every ridge and every valley with millimetre precision. On our screens, these maps emerge as ethereal, ghostly clouds of colour draped over the image of the galaxy cluster. This luminous haze, unseen by any eye or conventional telescope, represents the true architecture of the cluster. You can see how the visible galaxies are nothing more than bright specks of dust nestled within the deep gravitational wells of this vast invisible structure. The dark matter is not smoothly distributed. It is clumpy and complex, with a dense central core and smaller subhalos that correspond to the locations of individual galaxies, each one trapped in its own private gravitational cocoon. This is not a simulation. This is not a theory. This is a direct observation of the invisible universe. We are for the first time truly seeing the unseen. And with this new vision comes the power to test our most fundamental understanding of the cosmos. Our leading theory, the lambda-Col dark matter model, makes very specific predictions about how dark matter should behave, how it should clump together, and what the density profiles of these halos should look like. Now we can finally put those predictions to the ultimate test. Does the intricate structure we observe in these maps match what the theory predicts? Are there discrepancies, small deviations from the model that could hint at new physics at a more complex nature for dark matter than we have ever imagined? Every new lens system discovered by Webb becomes another page in this test. We are placing the foundations of modern cosmology under the most powerful microscope in history. The central conflict, the initial apprehension that these duplicated images were merely a confusing cosmic artifact, is now completely resolved. The mirage is not the problem. The mirage is the solution. It is the ultimate diagnostic tool, a celestial scalpel, that allows us to simultaneously perform astrophysics on the most distant objects in the universe and conduct fundamental physics on its most mysterious invisible components. The light from a single, impossibly remote galaxy, after a journey of over 13 billion years, is intercepted by a cluster of galaxies. Its path is bent, its image is shattered and magnified, and it continues for another few billion years until it is collected by our golden mirror orbiting the Sun. And in that single photon's journey, in its final distorted arrival, we find the answers to three of our most profound questions. We see how the first galaxies were built, a chaotic and violent process of cosmic construction. We witness the very moment the universe was illuminated, the fog of the Dark Ages burned away by the first generation of stars. And we are given a map of the invisible, a ghostly blueprint of the dark matter that dictates the fate of the cosmos. This is the scientific harvest, the breathtaking climax of our quest. The duplication of a galaxy is not a redundancy. It is an amplification. It transforms a single faint spark from the dawn of time into a Rosetta Stone of cosmic history. It takes the feeble light of a single celestial body and uses it to illuminate the entire universe, from its chaotic beginnings to its invisible architecture. We sought to understand a strange echo, a curious reflection in the cosmic mirror, and in doing so we found ourselves looking at the very machinery of creation. The illusion has delivered the ultimate truth, granting us a clarity we thought was unattainable. But this newfound clarity does not bring an end to the mystery, for with every veil we lift, another more intricate one appears just beyond. The light from this cosmic mirage has answered so many of our questions, but it has also begun to whisper new ones, hinting at deeper complexities in the cosmic dawn and subtler features in the dark universe that we are only now beginning to comprehend. The map is not the territory, and our journey has only just begun. And so the phantom galaxy hangs there in the digital abyss, its light splintered and smeared into an impossible ethereal arc. We have journeyed with its ancient photons across 13 billion years, witnessing their path bent and magnified by an unseen cosmic hand. What began as a flicker of dissent in the mind of a young patent clerk, a wild thought experiment about falling elevators and curved space-time, has now been rendered in breathtaking luminous detail by our most ambitious eye in the deep heavens. The journey from that abstract equation, a mere whisper of chalk on a blackboard, to this tangible, shimmering ghost from the dawn of time represents one of the greatest intellectual odysseys our species has ever undertaken. It is a story of defiant curiosity, of relentless pursuit, a testament to our innate refusal to accept the universe as it merely appears. We demanded to see behind the curtain to understand the machinery, and in return the cosmos revealed a principle of such elegance and power that it would forever change how we see everything. This cosmic mirage, this beautiful lie, has become our most profound truth. It is the universe holding a mirror up to its own infancy, and we, after a century of dedicated looking, have finally learned how to focus it. This gravitational lens is not simply an intellectual curiosity anymore. It has been transformed from a footnote in the grand theory of relativity into the most powerful magnifying glass we've ever known. It is nature's own telescope, forged not from polished glass and metal, but from the crushing invisible weight of a galactic leviathan. Its aperture is not measured in meters, but in hundreds of thousands of light years. Its focal length stretches across unfathomable distances, perfectly positioned by chance and cosmic evolution to grant us a godlike view. When you gaze upon that warped image of the distant galaxy, you are not looking through the James Webb Space Telescope. You are looking through an entire galaxy cluster using its collective gravity as the primary optical element. The JWST is merely the sophisticated eyepiece that allows us to witness the spectacle. This natural observatory performs feats our own technology cannot yet dream of. It plucks the faintest, most remote objects from the brink of invisibility, galaxies so distant their light is little more than a whisper, and amplifies their presence, making them blaze forth for our study. It allows us to resolve details in the universe's nascent structures, to see the clumpy, chaotic beginnings of star formation in the first billion years, a level of clarity that would otherwise be utterly unattainable. We are in a very real sense peering back through the grandest of keyholes, a tiny opening in space-time that reveals the universe as a toddler, taking its first incandescent steps out of the cosmic dark ages. The light from this mirage began its journey when the cosmos was a shadow of its present self, a younger, hotter, more compact and violent place. Every photon carries with it the fossilized information of the bygone era, a time capsule delivered to our doorstep by the patient courier of gravity. And by carefully reassembling these distorted apparitions, by meticulously reverse engineering the gravitational warp, we are learning to read the story written in that ancient light. We are no longer just cataloguing the stars, we are practicing cosmic archaeology. Yet as with every great discovery, this spectacular image answers one question only to pose a dozen more, each more profound than the last. The era of gravitational lensing is not culminating, it is just beginning. This cosmic mirage is not an endpoint, but a signpost pointing the way toward deeper, more fundamental mysteries that still haunt the peripheries of our understanding. The very tool that has granted us this unprecedented view is now being recalibrated to hunt for the universe's most elusive spectres. Our next great quarry is the invisible. Think of the delicate, precise way this light has been bent. That distortion is a direct signature of the total mass that bent it, both the mass we can see in stars and gas, and the mass we cannot. For every point of light in that foreground cluster, there is an ocean of darkness surrounding it, a substance that emits no light, reflects no radiation, and interacts with our world only through its immense gravitational pull. We call it dark matter, a name that speaks more to our ignorance than our knowledge. It is the invisible skeleton upon which the visible universe is built, the silent scaffolding that dictates where galaxies form and how they evolve. Until now, its presence has been inferred indirectly through the strange rotation of galaxies or the motions of clusters. But with these powerful lenses, we're moving beyond inference. We're beginning to map the invisible with staggering precision. By analysing the exact shape and intensity of the warping in images like this one, we can create a topographical map of gravity itself. We can chart the invisible clumps, the unseen filaments, the vast dark halos where this mysterious substance congregates. It's like dusting for fingerprints at a cosmic crime scene. The dark matter leaves its gravitational signature on the very fabric of light. The JWST and the observatories that will follow are becoming our forensic toolkit. Each new lensed image is another piece of the puzzle, another region of the sky where we can stain the invisible, revealing the true dark architecture of the cosmos. We are no longer just looking at the universe. We are learning to see its hidden, more massive counterpart, and in doing so we inch closer to understanding what this ghostly material truly is. Is it a new particle? A creature from beyond our standard model of physics? Is it a flaw in our understanding of gravity itself? The answers are encoded in the subtle gravitational shear across billions of light years, and we are finally building the keys to unlock them. And if dark matter is the universe's hidden skeleton, then dark energy is its phantom heartbeat, the force driving its inexorable acceleration. This perhaps is the single greatest mystery in all of science. We see its effects everywhere. The fabric of space-time is not just expanding, it is stretching apart at an ever-increasing rate driven by a repulsive force inherent to space itself. It is a cosmic anti-gravity pushing everything apart, a force that will ultimately determine the universe's final fate. But what is it? Where does it come from? Is its strength constant, or does it change over time? Here too, gravitational lensing provides a crucial and perhaps unique window. The geometry of the universe, its very shape and expansion history, directly influences how light bends as it travels through it. A universe with more or less dark energy will lens light in subtly different ways. The distance to a lensed object and the distance to the lens itself are both affected by the cosmic expansion history. By studying lensed systems at different distances at different epochs in cosmic history, we can measure the changing rhythm of that expansion. We can effectively take the universe's pulse at different points in its life. Does the lensing effect grow stronger or weaker in a way that our models predict? Or are there deviations, subtle anomalies that hint at a more complex, perhaps even more terrifying nature for this dark energy? Could it be a phantom energy that will grow in strength until it rips the universe apart in a big rip? Or will it fade, allowing gravity to reclaim its dominion? These are not just academic questions, they speak to the ultimate destiny of everything we know. The answer lies in the delicate statistics of cosmic mirages and comparing the degree of warping in the nearby universe to the distortions we see in the most ancient light from the cosmic dawn. Each lensed quasar, each distorted galaxy arc, becomes a new data point in our quest to chart the future of reality itself. The very illusions that once baffled us are becoming our instruments for prophecy. But perhaps the most tantalizing promise held within these gravitational funhouse mirrors is the chance to witness the universe's first breath of light. Before the first galaxies, before the first stars, there was darkness. For hundreds of millions of years after the Big Bang, the cosmos was a sea of neutral hydrogen, a uniform lightless fog. Then somewhere in that primordial murk, the first stars ignited. They were not like our sun. They were monsters hundreds of times more massive, forged from pure hydrogen and helium. They burned for only a fleeting few million years, blazing with a ferocious blue-white intensity that was 1,000,000 times brighter than our own star. These were the Population 3 stars, the first generation of the cosmic pioneers. They were the crucibles that forged the first heavy elements, the engines that began to ionize the fog and make the universe transparent, paving the way for all the structure and life that would follow. To see one of these stars, to witness the moment of first light, has been the holy grail of observational cosmology for decades. Yet they are impossibly far away, impossibly faint, impossibly brief. No telescope we could ever build, not even one the size of a planet, could hope to resolve a single one of these primordial suns directly. But a gravitational lens can. By a staggering fluke of cosmic alignment, a natural telescope could in theory magnify a single solitary star from this first generation to the point of detectability. It would be the ultimate cosmic needle in a haystack, a flicker of light from the edge of time, its image momentarily stretched and brightened by the gravity of a foreground galaxy cluster. We have already had a taste of this with the discovery of Earendel, a star from a very early generation magnified into view by this very process. It was a dress rehearsal for the main event. Now with the JWST's infrared sensitivity, we are actively hunting for its ancestors. We're staring into the deepest, most powerfully lensed regions of the sky, waiting and watching for a new point of light to flare into existence, a ghost from a time before galaxies as we know them even existed. Finding such an object would be transformative. It would no longer be a theory. It would be a reality, a single point of light that tells the story of how the universe woke up from its long slumber. We would be witnessing the genesis of chemical complexity, the very dawn of matter as we know it. Through a cosmic illusion, we would capture the universe's opening act. And so we find ourselves in a new epoch of discovery. The great observatories of the future, like the Nancy Grace Roman Space Telescope, are being designed with this principle at their core. They will survey vast swathes of the sky, hunting for these gravitational lenses not one by one, but by the thousands, turning this rare phenomenon into a robust statistical tool. We will create a new kind of map, a chart not just of the stars and galaxies, but of the warps and wefts in the fabric of spacetime itself. We stand at a precipice looking back to the very beginning and forward to the ultimate end, using the universe's own gravity as our guide. The journey has been immense. From the seed of an idea in one human mind, a concept so counterintuitive, it was initially dismissed as a mere curiosity, we have reached this moment. A moment where cosmic mirages, these grand celestial deceptions, have become our clearest and most indispensable windows into the fundamental nature of reality. They are the key that unlocks the dark sector of the universe, the magnifying glass that brings the cosmic dawn into focus, the oracle that may yet tell us our ultimate fate. These beautiful warped images are more than just data. They are a profound reminder of our place in the grand unfolding story. They teach us that the universe is not only stranger than we imagine, it is stranger than we can imagine. And yet through reason, through curiosity, through our relentless desire to see what lies beyond the horizon, we have found a way to make its secrets our own. The cosmos, it turns out, is a magician of infinite subtlety, and we are finally, after all this time, learning to see the method behind its magic. The mirage is real, and it is showing us everything.